Up till now, we've been focusing on having the robot balance. That's great, but what if we want it to do a little more than that? Disney uses Steam decks to control their BDX droids. I want to do something similar with our balance bot. This requires a bit of extra engineering, as it means we need to modify the observation vector. In other words, the agent takes in a command as part of its input, combines it with all the other sensor readings, and provides suggested motor controls. We want the robot to listen to those commands and still be robust enough to handle terrain that it didn't see during training. Let's get started. In the previous 4 episodes, we worked on training a robust agent that could balance even with imprecise 3D models and random environmental factors. We're going to continue building on those concepts by adding commands to our training setup. This will require reworking the environment and training phases. By the end of this episode, we should have a robot that can move around as well as balance. We will work on deploying the agent in the final episode, as that requires implementing a custom Wi-Fi access point and web page on the ESP32. As a refresher, here is what our reinforcement learning training loop looked like previously. Our observation vector included the pitch and pitch rate from the IMU, along with the motor encoders for the wheels. We also used this information to create our reward function. We're going to change this so that the observation vector now includes 2 commands, the forward and backward velocity along with the turn or yaw rate. We'll also need to update the reward function, but that's a little too complex to show here. I'll talk about that when we get to it in code. Speaking of code, let's take a look at our new environment. Let's go into part 5 in our software. We're going to look at our new environment that's going to add commands for us. Let's make sure we scroll up to the top so we can see what's going on. We've added a few new items to our domain randomization config class. Here you can see that we will pick velocities between some min and max for forward and back, and we pick some rotational velocity or yaw velocity between some min and max. We also have some probability of sampling and making those 0. I found from experience that if you set some values here like -1 to 1, the probability that you tell the robot to sit perfectly still is pretty close to 0. So every now and then, maybe like 30% or 50% of the time, whenever we sample a new command, we're going to say go ahead and just set it to 0 regardless, so that we can have the robot sit still for a good portion of training. We also have the probability of sampling a new command each step. This can be like 1% or 0.5% of the time, so that the robot gets that new command and it's like driving it around. So with that, we set them to essentially tell the robot to sit still by default, but we can change these in training as we slowly introduce domain randomization with our different phases for that curriculum learning path. If we scroll down to some of the new parameters here, you'll see that I've changed the reward function. So now we have a pitch rate penalty and a smoothness penalty. Together, those should encourage smoother transitions as the robot moves from one command to the next. We've also introduced this velocity and yaw reward coefficient, so that rewards the robot more for following a given command. In order to measure how much the robot is following that command, we essentially compare the command given versus what the robot is actually doing. So if we say go forward by some amount, the difference between how fast the robot is going forward versus that command, we plug that into an equation to get us some kind of difference tracking. We can adjust the penalty for not tracking that using these sigma values, and you'll see those in the reward function in a moment. We also have our maximum here. Remember that the commands are normalized, so these scale those commands to produce actual speeds that the robot needs to track against. You'll notice that we don't have position penalty or yaw penalty any longer. That was removed now that we have these commands. You can still use command velocity 0 and command yaw 0 to tell the robot to stand still. This is essentially generalizing the whole idea, but now we're allowing the robot to move around according to how we specify. Let's go down to reset. And in reset, we have this section where we optionally sample a new command for the episode. If that domain randomization config is not used, we tell the robot to stand still, just as we've done before. Otherwise, we're going to sample a new command uniformly from our range, the min and max that were given as part of that domain randomization config. Now, if we go down to step, we see all the domain randomization code that was added previously, but we are also adding the ability to sample commands mid-episode. This is like giving the robot a new direction or a new rotation from a remote control as it's driving around. We've also massively changed the reward function. So you can see it's a lot more complicated now. It is still a combination of staying alive, the pitch and pitch rate, the penalty, this new smoothness penalty, the position penalty, and then we've given it the tracking rewards here. So the idea is still the same. We're coming up with a sum of all of the rewards, including subtracting the penalties, to get a single number. But how we get there is a little more complicated than what we've been using in previous episodes. One of the things we need to do is get the actual forward velocity in the world frame in order to figure out how fast the robot is moving forward or back, regardless of its orientation. We get the yaw rate, as we've done before, and we're going to scale the normalized commands to actual rates. So our velocity, which is -1 to 1, is multiplied by our velocity max to get something in meters per second. Actually, this is not the case because this is meters per second and this one is radians per second. We then compute our penalties. So we've got our pitch penalty, which we've used before. The pitch rate penalty is just the pitch rate coefficient times the pitch rate squared. We want the robot to try to maintain its pitch as much as possible. And we're also telling the robot to try to stay upright as much as possible. Something you'll see here is that the robot's going to try to stay upright from the commands given. We could try modifying this in the future in order to keep the robot alive, but allow it to pitch some in order to move quickly forward or back. But for now, let's just try to keep it upright so we can drive it around. We also have our action penalty, similar to what we've done before. This tries to discourage jerky motion back and forth. And we've added this smoothness penalty to encourage the robot to smoothly move between different commands. Something interesting that I found is that we need to find where the new origin is whenever we tell the robot to stop. So wherever it stops, this becomes this new X and Y position, and we penalize the robot if it moves off of those, but only if the velocity and yaw targets are exactly 0. Otherwise, we don't penalize it because we're assuming the robot needs to be moving. We then save the previous action because it's what we use to compute the smoothness penalty here. The Gaussian rewards come from other researchers or other research projects that reward agents for taking specific actions. It uses this decay function in order to do that. So we have our coefficient. We subtract the actual from the target. So if we say move forward 2 meters per second, the actual measured velocity, which we got up here with this is privileged information, the difference of those is squared. So we get that absolute value. And then as the difference grows larger, that penalty grows even larger thanks to this squaring. We then divide by this sigma velocity. This sigma value controls how much we are penalizing anything that's off of a target. So it allows us to allow for some slop. So if we say move for 2 meters per second forward, the robot's not quite there. Larger sigma values penalize less. Smaller says penalize more so that the robot has to track the target more closely. We then take the negative of that, and then we get the exponent of that, so e raised to whatever that value was, multiplied by our coefficient. Together, if we're not including the coefficient here, let's assume that's 1. This gives us ideally 1 for perfect tracking, where there's no error here, and then 0 as the error grows. So that gives us something between 1 for it's tracking well to 0 for not tracking at all. This expression creates a smooth penalty function that gives us something between 0 and 1, and then we can multiply by our reward coefficient. in order to get that reward per step. We do the exact same thing for the yaw command and how well the robot is tracking. We then combine all of those to get our singular reward, that one value that's used in all of our computation for PPO. The render and close look the same. So with that, I'm going to save because I changed that one comment. And now we are ready to look at our notebook. In Jupyter Lab, let's go over to software. We're going to go to O5 commands, and we're going to open up this train with PPO command notebook. Much of this looks the same as it did from the previous episode where we introduced domain randomization. I'm going to run this first cell, nothing new here, except we're importing our new environment with the command functionality. I'm going to keep the number of environments and the steps per environment the same. In PPO, the only thing I've done is made the actor and critic a little bit bigger. You can probably get away with 32 nodes per hidden layer, but I was experimenting with slightly larger networks, and this seems to work just fine. And it doesn't seem to take any longer to execute on the ESP32, so we're going with 48 and 48. Creating the environments remains the same. This is our load agent that we use for debugging. In the first phase, we're going to teach the robot to balance. We don't care if it wanders around, so we have our velocity and yaw rewards set to 0. As long as it stays upright, it's accomplishing this phase. Then in phase 2, much like we've done in the past, we teach it to stay in place. So the domain randomization for the yaw and velocities default to 0, but we do introduce these reward coefficients and the sigma values here so that the robot learns to stay in place. Then we start adding in our velocity commands, which we do with the domain randomization config here. So we start off small. We say you're allowed to go back and forth at half speed in either direction, but you're still not allowed to turn yet. One of the things I found is that rather than trying to add commands after teaching the robot to balance in place with full domain randomization like we did in the previous episode, not only would that take something like 20 phases to accomplish, the robot really struggled with commands after learning all the domain randomization. So I found it better to teach it to accept commands, follow those, and then slowly start to mix in the various domain randomization things like varying the mass, varying the friction, and so on. So the mixture of the two for various phases seems to work the best for this. We're also going to tell the robot to stay still 50% of the time. So that's that 0 probability. So it understands what staying still looks like. Then in phase 4, we're going to introduce a small amount of yaw commands that's turning at half speed in either direction and allow for full velocity commands. If we scroll back up, one of the things you'll notice here is I've set the velocity max to 0.5. That overrides the default. So we're going a maximum of half a meter a second. So a command of -1 means go backwards at half a meter per second. That's what this is saying. We are leaving yaw at the default, which is 2 radians per second, which should be fine. After some playing around, I really couldn't get velocity faster than this. It struggles with trying to stay upright because that's what we're rewarding or penalizing rather. And the robot will tip if we try to go faster than about 0.6 or 0.7 meters per second. You're welcome to try playing with the reward function and seeing if you can get it to go faster, but this works well enough for now. As I mentioned in phase 4, we are allowing for full range of velocity with a little bit of yaw commands. Then in phase 5, we introduce mid-episode sampling. So previously it was just setting a command for the entire episode. Now every 0.5% of the time for each step, we are going to resample the commands, and we are allowing for the full range of yaw commands here. So once that's done, we move on to phase 6, where we start introducing the rest of our domain randomization. This is where we inject some noise into the observations from the sensors. We also introduce some delays, and we can vary those each episode. Phase 7 adds the motor noise and some random pushes. Phase 8 starts to vary the mass and the friction. Phase 9 varies the amount of motor gain, basically how much the motors can actually drive the robot, thanks to things like battery voltage drop. And phase 10 gives us our random axle torques in order to simulate the ridges on the tire. So this whole thing should take 10 phases, where if you notice, we start with our basic balance first. allow it to move around, then tell it to stay still, then we add commands, then we slowly add full domain randomization. So with that, let's start the training process. So we just ran that cell. So we're going to come back to phase 1. We're going to run this and then run train. That's going to pop up here with MuJoCo. There it goes. And I'm going to run all of these phases up until the evaluation part of phase 10. So once we get here, we're going to run train, but we're going to come back after this is done to see how the robot performs. And now we're just going to let it train. Once training is complete, feel free to go take a look at TensorBoard. It looks like the returns are decent, but jumping around a lot, but we should be able to get a solid model from this. If we go back here, run our evaluation, you can see the commands given. So first to stay in place, then it looks like drive around, and we'll let this continue for a few more episodes. And it seems like the robot's performing pretty well based on the commands given, not really falling down at all. So I'm pretty happy with this. And it's smoothly transitioning between the different commands. This looks really good. So let's close out of the environments. We will export the actor as an Onyx model, and then we will export it to raw C code. I know you probably want to see how well the robot performs when we deploy the agent to the real thing. I'm going to make you wait though. We need to develop a full access point and serve a web page that listens for commands over a WebSocket connection. We'll run this on the other core on the ESP32. Because this is more involved than just updating our agent, I'd like to spend the final episode showing you how to create this web page-based controller. See you then.